Hello, welcome to another lesson of sectoral structures theory. Today's lesson is not from any particular chapter in the book, but it will be a little bit of a foreshadowing of several chapters because it will help us to better understand some key concepts that will be in the later videos. So today we want to talk about functions of sectoral structures. We've already seen several. You will notice in the book we will refer to them either as mappings or transformations, which we will go back to. For example, we saw the partial sums transformation. However, now if we want to look at the very big picture, we will talk about functions. And we will show the different types of functions related to sectoral structures. And then as we go into the following chapters, we will talk about specific types. So we will see things like structural mappings or sectoral transformations and all these different things. So let's begin by really talking about the very broad classification of functions of sectoral structures. Or maybe we can call them mappings because the first big category of these mappings will be called functions. So these will be called the sectoral or sectoral structure functions. So when we talk about a function of a sectoral structure, or alternatively a transformation or a mapping, we're really talking about a function f bar. So we will use this bar whenever we're talking about functions of sectoral structures. So we will say f bar of an, so a function applied to a sectoral structure an to give us another sectoral structure bn. So we started with a sectoral structure, we ended with another sectoral structure, and we will say this is, we can either say from stn to stm, small letters, or alternatively we can say from st capital N to st capital N. So that means that f begins in the set of sectoral structures and ends in the set of sectoral structures. So we've seen several of these so far. We've seen, for example, the sigma bar function, which is the partial sum function, where we start with a sectoral structure and we end up with another one. We've seen the dal function, which is basically the reduction of a sectoral structure to its irreducible form. And we've also seen the conjugate of an. We can think of that transformation also as a function, where we start with a sectoral structure and we end up with another sectoral structure. Now these can also be further classified. We're going to see a lot of ways throughout the book. However, I want to talk about two main categories. First, and perhaps the most important distinction is, does the sectoral function preserve the order of the sectoral structure? So if we start with a sectoral structure of order 3, does the resulting sectoral structure also have an order of 3? Remember, order is lambda. If it does, we will call these homogeneous functions or homogeneous transformations. And this will be a concept that we will carry throughout our discussion of sectoral structures theory. So if lambda of an and lambda of f of an are the same, then we say that this is a homogeneous function or a homogeneous transformation. For example, dal of an, which is the reduction of an, gives us a sectoral structure that has the same order. So therefore, this is an example of a homogeneous sectoral function. If the order is not preserved all the time, so even if it's preserved sometimes, that doesn't count. So if it is not always preserved, then we say it is non-homogeneous or inhomogeneous function. For example, sigma bar, we know that by definition, the partial sums transformation reduces the order by 1 unit. So therefore, this is not a homogeneous function. Similarly, the conjugate function is not homogeneous as well. However, the involute function, which we've done a video about earlier, is homogeneous because it does preserve the order of the function. So that's the first broad distinction. When we look at the algebra of sectoral structures, we will see why we call that homogeneous. Secondly, we will talk about homeomorphic functions. And again, this is a name that implies topologic transformation. And again, when we talk about folding and unfolding of sectoral structures, it will make sense why we picked this name. However, homeomorphic functions or homeomorphic sectoral functions are ones where the the degree n is preserved. So the degree n is preserved. So that means we stay within the set st subscript n. So this is the small n when we apply the transformation or the function. So instead of using the capital N, we can say small n. If that is the case, then we say this is a homeomorphic function. And usually when we talk about homeomorphic, we think of a topological change. And this is indeed the case, as we will see in future chapters. So is sigma bar homeomorphic? No, it's not, because the degree of the resulting function changes. Is dal homeomorphic? Again, it is not, because the degree changes. However, this, which is the conjugate function, is indeed homeomorphic, because the degree of the conjugate is equal to the degree of an, even though the order is not. So let's look at these three one more time. So the partial sum, that one is not homeomorphic and not homogeneous. Dal is homogeneous but not homeomorphic. Conjugate is homeomorphic but not homogeneous. The involute is both homeomorphic and homogeneous. So it preserves both the order and the degree. It's also, we will call this type of function conformal, but we don't need to get into it at this point. So these are the types of functions. Let's look at a simple example. Let an equal to wi, which is the weight of I, from I equals 1 to lambda. We close brackets, subscript n, and let f bar of an equal to 2wi plus 1 from I equals 1 to lambda. So this type is very simple. It's a linear function. In this case, let's take the example of an equals to 312 subscript 6. We apply this change to each part. So we get 7. So 3 times 2 is 6 plus 1 is 7. 1 becomes 3, 2 becomes 5, and n becomes 15. So we notice that the order was preserved, but the degree was not. So this is homogeneous, but not homeomorphic. Similarly, let's apply the same function to 1 to the 4th subscript 4. 1 becomes 1 times 2 plus 1 is 3. So this becomes 3 to the 4th subscript 12. Again, the order was preserved, but the degree was not. Now, if the function was of the form n times wi without adding anything, then this would always produce an isomorphic sectoral structure. So isomorphism is a type of function that is homogeneous but not homeomorphic. So this is the first broad category. Again, this is just an overview. Now let's look at another broad category, which are called sectoral functionals. So this type of classification is not really detailed in the book. I'm doing this in the video, but they're explained without really doing this type of classification. So sectoral functionals are functions or transformations applied to a sectoral structure. However, the result is not another sectoral structure, but rather a real number. So we've seen many examples of these so far. We've seen the diagonal function, which is simply the diagonal, which is the linear distance between the two delta joints of the sectoral structure. So this will usually give us, it could be a natural number, it could have radicals, it could be a pretty complicated number, but it's always a real number. So we will say that d bar of an is an example of a sectoral functional. We start with a structure, we end up with one number. Another very simple example is if we consider lambda of an as a function, so the order of an. So in this case, the order is 2. So we started with a sectoral structure, we ended up with just a single number. So this is also a functional, as is n of an, which is the degree of an. A more interesting one would be the boundary of an. So if we want to take the length of the boundary, which equals to 2 pi plus 2 lambda, as we've seen before. So in this case, lambda of an would be 2 pi plus 4. So it gives us a real number, not a sectoral structure. Let's look at another example that's slightly more complicated. So let f of an equal to boundary of an divided by the order of an. And let's use the example of sectoral structure 4, 2 squared, 1 squared, subscript 10. So we will apply this. We will say the boundary is equal to 2 lambda plus 2 pi divided by the order. The order is 5. So this equals to 2 plus 2 pi over 5. So again, we ended with a real number. So this is another example of a sectoral functional. Now, when we're talking about functional, it doesn't really make sense to talk about homogeneous or homeomorphic and homogeneous, because the result is a single number. So we would call this type as functionals. Now let's look at another interesting example. So let's define the function g bar of an as, instead of saying equals to, we will say isomorphic to wi divided by 2, so very simple, from I equals 1 to lambda. And let's look at an example. Let an be 4, 2, 3 subscript 9. If we apply this, we get 2, 1. So 4 divided by 2 is 2, 2 divided by 2 is 1, 3 divided by 2 is 1.5. So we notice here that these two are natural numbers. This is not a natural number. And there's no such a thing as half a sector in sectoral structures theory. The least you can have is 1. So this is not a sectoral structure. So G bar of AN does not always yield a sectoral structure. So therefore, we cannot just call this as a regular sectoral function, because it's not. However, we notice that G bar of AN is isomorphic to a sectoral structure. So if we multiply all of these by 2, we get 4, 2, 1.5 times 2 is 3, which is what we started with. And there are more solutions, of course. But so G bar of AN is isomorphic to AN. So let's take a second to think about this. So G bar does not always give us a sectoral structure. So therefore, it is not a regular function. However, it always gives us a result that is isomorphic to a sectoral structure. So for this reason, we call this type of mapping an isofunction. In other words, we're saying this is not really a regular sectoral function or an ordinary sectoral function. It is a special type, because it only works if it includes an isomorphism relationship, not an equality. And this is, if you recall, a big part of sectoral structures theory is many times we look at what is isomorphic, not necessarily what is equivalent. So if f bar is a function or a mapping from Stn to Stn such that, and we will say here f bar of An equals m in this case was this, where m does not belong to Stm. So let's decompose this. So we're saying that when we apply the function to An, we get a result that is not a sectoral structure. However, f bar of An is isomorphic to a sectoral structure. So this is what we call an isofunction for a sectoral structure. We get a result that is not a sectoral structure, but it is isomorphic to a sectoral structure, and therefore we say that this is indeed an isofunction. We're going to look at another example that is very useful for us, and it is why we need to define isofunctions. And that is, we're using this symbol of an angle here. I might have used something different in the book. So we will say this will be read as the arc form of the sectoral structure. So if you think about it, the sectoral structure, each part corresponds to an arc. So if we want to write it in arc form, so instead of writing it as a set of natural numbers, we will write it as a set of arc length that add up to 2 pi. So the arc form of An is equal to Ci. C here is the arc length of part I from I equals 1 to lambda. And if you look at it, it's very easy to figure out the arc length by figuring out what the length of phi, if you remember we talked about phi at the very beginning, is. So phi is the arc length corresponding to the number 1 in a sectoral structure. So let's see this example. So here we have the sectoral structure 3, 1, subscript 4. So we want to figure out what arc length corresponds to a part that is equal to 1. And that's very simple. We say phi equals to 2 pi divided by n. So in this case, n is 4. 2 pi divided by 4 is pi over 2. Now, if we want to figure out the length, the arc length for any other part, we simply say Ci is equal to phi times the weight of that part. So this one has a weight of 3. 3 times pi over 2 is 3 pi over 2, which is indeed the arc length. So therefore, we will say that the arc form of AN is equal to Wi times phi from I equals 1 to lambda, and then instead of n we write 2 pi. So let's do an example. AN is equal to 4 to 1 squared subscript 8. Therefore, phi is equal to 2 pi over n, which is 2 pi divided by 8, which is pi over 4. And we apply this rule to figure out the arc length. We say that the arc form of AN is equal to 4 times this, so that's pi. 2 times this, that's pi over 2. And then pi over 4, subscript 2 pi. Now, of course, none of these are natural numbers. And this is not really a sectoral structure when we write it in this form. So we will not call it a function. However, this is isomorphic to sectoral structures. If we divide everything by pi, and if we multiply everything by 4, then we find that this is indeed isomorphic to the sectoral structure 4 to 1 squared subscript 8. So the arc form of a sectoral structure, which will be very useful for us in the future, it's basically listing the arc length of all the different parts, is an example of an isofunction, because it gives us a result that is not a sectoral structure, but it is isomorphic to a sectoral structure. Also notice that this type of isofunction preserves the number of parts, so it is homogeneous. Now finally, we will talk about sectoral functors. So a functor in this sense takes a sectoral structure and gives us some other structure or some other object that is not just a simple real number, and it is not a simple sectoral structure either, nor can it be isomorphic to a sectoral structure. So we start with the simplest example would be f from stn to r to the x, where in this case r to the x means a series of real numbers that are not that cannot be simplified to a sectoral structure. Or it can be some other object altogether, as we will see with another example where we can correlate it with geometric objects in the future. So in this case, f of an gives us a structure M that does not belong to STN, so it is not a sectoral structure, nor is it isomorphic to a sectoral structure. So for example, let's define S bar of AN is equal to sine of the arc of the given part I from I to lambda. So let's use the same example, 4 to 1 squared subscript 8. We write this in the arc form. So the arc form of AN we saw is pi, pi over 2, pi over 4, pi over 4. And then S bar of AN would be the sine of each of these arcs. So we get 0, 1, square root of 2 over 2, square root of 2 over 2. And this will be useful for us in the future, this type of function. But notice that there is no way to express this sequence as isomorphic to a sectoral structure. And even if it worked for a certain example, it's not going to work for other examples as well. Sometimes we will also end up with negative numbers or with zeros, as in this example, so it's not going to work. So we call this type of relation or this type of mapping as a functor, a sectoral functor. And in fact, in the very next video, we will be going back to this particular type of relation. Let's look at another example and try to determine what kind of relationship this is. I also want to mention that for these sectoral functors, we can also say that they're either homogeneous or non-homogeneous, depending on the number of parts. Okay, let's define sine bar of an as being the absolute value of the sum of sine ci. We're also going to apply another layer of complication where we will alternate between positive and negative, where we will multiply either by 1 or by negative 1, depending on the term. So we will say negative 1 to the power of I plus 1. And you will see we studied this particular relationship in chapter 6 of the book. So let's look at sine bar of 4 to 1 squared subscript 8. We've already figured out what the signs are. Now we just need to apply this relationship. So we'll say 0 minus 1 plus square root of 2 over 2 minus square root of 2 over 2. We get negative 1, we take the absolute value, and the result is 1. So this is in fact a functional and not a functor. So this is one way where we can start with the sectoral structure, do a relationship on the arc length, and end up with this single number. So this was an introduction, a very general overview. But now, as we go on to see more transformations and more mappings, we can start to think of, is this a function? Is this a functional? Is this an isofunction? Or is this a functor? Also, we will start keeping in mind particularly whether the relationships are homogeneous or non-homogeneous.